Okay, so we're back to the interior of the Earth, and I would like to first acknowledge my contributors, graduate students and postdocs of mine in the last few years. In 1968, I was not even dreaming of becoming a geophysicist. I was studying mathematics and in the first row for another revolution here on the Boulevard Saint-Michel. So plate tectonics managed to explain a lot of phenomena, the distribution of earthquakes around plate boundaries, and of course the volcanism in plate boundaries, different plate boundaries, both ridges and subduction zones. But it still left a puzzle, which is the intraplate volcanism, such as the one here shown in Hawaii, where with a line of volcanoes of increasing ages in the direction of the motion of the plate. And Tuzo Wilson in 1963 proposed the model of the hotspot plume, Mantle plumes, where the origin of this volcanism was a plume of material rooted somewhere in a boundary layer inside the Earth and fixed, and the plume is fixed with respect to the motion of the plate over it. And then Jason Morgan, in 1971, proposed that this boundary layer inside the Earth's mantle would be at the core mantle boundary. As yesterday we heard from Francis Albared, the volcanism, the mid-plate hotspot volcanism, is quite distinct from that of mid-ocean ridges, in particular in its isotopic composition of trace elements. It's also, this model of plumes is something that has been observed for a long time, both in experiments and in numerical computations of fluids, heated iso-viscous fluid heated from below, where you see these narrow plumes of hotter than average material rising through the medium with a very big head. And in this simple kind of models, the expectation, when you scale it to the case of the Earth mantle, would be that the plumes would be very narrow, maybe 100 to 200 kilometers thick. And so for many years after that, the emphasis has been on trying to actually find those plumes. And it has been quite a controversial topic in maybe the last decade or two, fueled maybe by the propensity of Don Anderson to like controversies, the alternative explanation being for the hotspot volcanism being a very shallow, lithospheric, basically crack kind of hypothesis. So I think it is fair to say that we are now reaching a time where we can say where seismic tomography is becoming sharp enough, resolving enough, that we can say with quite some assurance that plumes do exist. And so I will give you the bottom line of the talk first. The mantle plumes do exist, but they're not your standard, at least the ones that we can resolve today, are not your standard plumes, narrow, thin plumes with big heads. They are rooted at the core mantle boundary, and they are clustered within the large low shear velocity provinces of the lower mantle. I will discuss this a little bit. And they cannot be purely thermal. They are too big to be purely thermal, and so we have to invoke some thermochemical processes, perhaps also partial melting, and perhaps also involve some non-Newtonian rheology for the lower mantle. And one of the interesting things is that their current morphology, not quite well resolved yet, but it highlights some of the the presence of a more vigorous convection in the upper 1,000 kilometers of the mantle and a very sluggish lower mantle. So why has it been so difficult to image plumes? There are two main challenges. First of all, for tomography, the principle of tomography is that you can illuminate a region from many different directions, which allows you to resolve the placement and the strengths of an anomaly, especially here is an example. So you need many observations in many different directions. Whereas on the Earth, especially with the location of hotspot volcanism in the middle of oceans, the geometry is not quite favorable. The earthquakes are on the boundaries of the oceans, the islands are in the middle, and there are not many crossing rays that will give you high resolution. There is not enough aperture unless we would be able to install very big arrays of seismometers on the seafloor. That's the first challenge. The second challenge is that if you have a narrow, thin, low-velocity body, a body that slows down seismic waves that go through it, actually the first waves that go through this region, they go around the low-velocity body. They don't go through it. So if you only measure the first arrival of the wave, like a P wave or an S wave, you miss the low-velocity body, or you image it as much weaker than it really should be. This is called wavefront healing. And in order to be able to really image it, you need to go deeper, to dig deeper into the waveform, the arrivals of the ripples behind the first arrival. Nevertheless, it has been quite possible to show that below hotspot volcanoes, such as here shown in Iceland, there is a low velocity zone looking like it could be the top of a plume. Here is work by Richard Allen and collaborators at Princeton showing the velocity of P waves beneath Iceland. This is an absolute velocity showing the relationship with the crustal structure. This is relative velocities to show the relationship of the low velocity anomalies with the surrounding. So down in this example, down to 400 kilometers, there is some continuation of this, or there is a route to the hotspot. A paper that attracted a lot of attention a few days later is the work by Mantle, Husnolet, and Tony Dahl and collaborators at Princeton again, who were able to develop a technique which allows for accounting for wavefront healing, and developed global models of P and S wave, but travel time tomography, still using the travel times of the best resolved waves, which are the first arriving P and S body waves that travel through the mantle, and showed these pictures of in different under different hotspots with continuing structures of low velocity all the way down to the core mantle boundary. Now, this was very interesting. They also pointed out that these features were quite broad, a few hundred kilometers, maybe 400 or 500 kilometers at least wide, which was hard to explain with a purely thermal model, and basically required a very high temperature contrast. The other problem from the skeptics' point of view was that if you look at these cross-sections of these plumes, quote-unquote plumes, if you are a believer, you will see the continuity of these structures from the core mantle boundary to the hotspot. But if you're a skeptic, you would say, well, there are some discontinuities here, and why is this blob part of it and not this other blob? So the controversy continued. There were attempts to obtain a sort of a larger aperture around specifically here the Hawaiian hotspot where, with tremendous effort, a large array of ocean bottom broadband seismometers were installed, a couple of 100 kilometers around the islands, leading to models, to a model in particular here shown by Wolf et al., which I'm showing in two cross sections from their paper, where again you can see that in the first maybe 200 to 400 kilometers there is no doubt that there is a column of lower than average velocity material, and in some cross sections it's also clear from these pictures that there seems to be a continuation downward. However, again for the skeptics, because of the aperture is larger, but it's still not large enough to really cover with crossing rays all the way down to the base of the mantle, the skeptics would say, well, there is smearing along the ray paths that are not crossed by other ray paths. And so even though this showed this feature going down into the deep mantle, it wasn't completely accepted. Meanwhile, so this is one type of tomography, which is a P-wave travel time tomography, which is able to look at rather small details, but doesn't have a very good view at the global scale of the large-scale feature. Another type of tomography, I can't go into the details of the techniques, but it involves longer period seismic waves, was able to get fewer details, but with a very robust determination of the long wavelength structure. And here I'm showing one model. I'm not even sure which one it is because they're very similar to each other at the scale of a shear wave velocity model as a function of depth. I'd like to point out at 100 kilometers, this is one verification of plate tectonics. This is really an image showing you see very well the ridge system. You see the cooling of the Pacific plate. You see the old cold continents. As you go deeper in the mantle, you continue to see the subduction zones, and these are cross sections from different models. I will point out that, because I will use this later, that in most regions, if not all, the subduction zones at the present time stagnate at either 660 or on a deeper horizon of around 1,000 kilometers. And then at the base of the mantle, the structure completely changes and is replaced by a ring of fast velocities with two antipodal equatorial large low velocity regions, which are, for a better name so far, called the large low shear velocity provinces. And many models have been developed, and this is very stable. This is a voting map saying that if all 5 models agree that the velocity is faster than average, it's blue. If it's lower than average, it's red. And you see come out this very good agreement between the models highlighting those large low shear velocity provinces. And if you extract, these are just examples from different models showing the same thing at large scale with some minor differences. If you extract the longest wavelengths, and here projected in a sort of 3D picture, you extract this so-called degree 2, showing that these large low shear velocity provinces plot in such a way that the ring of fast velocities contains the paleopole locations for at least the last 250 million years, implying that these structures have been stable, also based on some moments of inertia arguments, have been stable for a long time. There has been also observations, this is one from one of our papers, but that the hotspot distribution, which is indicated here by the black circles, correlates with this long wavelength. This is the distribution of hotspot, but it correlates with the distribution of shear velocity at the base of the mantle, so the large low shear wave velocity provinces, and also with shear attenuation in the transition zone. So you have this continuity from the base of the mantle to the top at these very long wavelengths. Here's an image of shear wave tomographic model at the same scale, but maybe more recent model showing the entire scales available in the model, showing depth cross sections through the mantle from the surface to the core mantle boundary, across cross sections across two South Pacific hotspots, McDonald and Pitcairn, and you can see that there is something that looks like it might be a plume-like feature connecting to these hotspots, but if you're skeptical, you would say, well, the color is on the other side. There's also other blobs of yellow, so why? What is this? Is this really continuous? Now, I will show you that with the current capabilities of waveform tomography, we can start resolving these features much better. And we address both of the challenges of imaging plumes, first by using the complete seismograms, not only some limited information contained in P and S waves, and this allows us to illuminate the Earth's mantle from many different directions, from all the bouncing waves around. We also can use the ripples behind the main phases to better image the effects of small-scale structure. And this, while this was possible already 25 years ago when I started doing waveform tomography, recently it has been made possible by the capability of computing numerical synthetics in arbitrary 3D structures that are very precise. And so this is a technique that is now very much evolving, and I will show you that it does lead to some interesting results. So this is a comparison of the model I showed you before, same cross sections, but with now full waveform tomography. What you see is that these features are basically the same as the ones that already existed in the previous model, but they're now much more well resolved and much more clear. And in particular, you can really see that in this cross section that covers half of the world, there is only one such feature in one of these cross sections, one big kind of conduit cross rooted at the base of the mantle and ending up in the vicinity of these hotspots. We see them in many places. I have to go fast. Here are specific ones across different cross sections. They also continue in the upper mantle and then all the way to the base of the plate kind of system. And I have to move on, I guess. There are also in the Atlantic and also recently imaged in higher resolution using waveform tomography in the upper part of the mantle, but confirming the large-scale features. And basically, all of these features in these models are all inside the large low shear velocity provinces. This is a map at 2,800 kilometers of this particular model, and all these circles indicate, the black and the gray ones indicate where we have such features, such conduits. Whereas those hotspots that are in the blue here, that are indicated by green, do not have a corresponding feature in the lower mantle, at least not a big one. So we can examine quickly what the characteristics of these plumes are. And I forgot to say that until recently, the debate about the plume hypothesis was really between in the realm of geodynamicists who were making models and geochemists who generally liked the model. But now I think we're back the other way around, is that seismology, of course, can still improve the modeling, but we're back to handing it over to geodynamicists to explain. So these plumes are broad. They're too broad, so this confirms what Husnollet was saying a number of years ago. They are too broad to be thermal plumes. They may be narrower, but if they are narrower and just purely thermal, the temperature difference we can calculate, estimate, would be like 1,500 degree contrast, which is quite unrealistic. So you have to invoke something else going on to be able to observe them. They're not perfectly resolved, but they are quite strong. They are quasi-vertical in the lower mantle. You see there is not much mantle wind in the lower mantle that would deflect them, and they are often laterally displaced from the corresponding hotspots up to about 1,000 to 2,000 kilometers, and this offset occurs at about 1,000 kilometers depth, not very regularly, which is something reminiscent to what geodynamicists obtain when they do a computation of a convective system with a change in viscosity between here a factor of 10 jump at 660 kilometers depth in a model which also contains a dense basal layer, so a compositionally different basal layer. I would like to point out that the same happens in subduction zones. The plumes get deflected, they get trapped for a while, but the slabs in some regions also do the same. So this is a new kind of emerging puzzle, what is going on at around 1,000 kilometers. Going back to the plumes, they are rooted in mostly isolated patches of low velocity here at the base of the mantle. Tomography is still not quite able to resolve the fine-scale structure of these patches at the core mantle boundary, but we can model that using forward waveform modeling. And in particular, we have found under some of these plumes very large extreme kind of structures, which we called ultra-low velocity zones, which have been found in other places in the Pacific, at the base of the Pacific Ocean. But what's special about this is this one in Hawaii and the other one I will show in Iceland is that it is very large. Its diameter is about 900 kilometers, and in this modeling, very simple modeling, we're able to model it by a cylindrical feature, even though we didn't have quite the kind of data that would allow to determine or constrain its shape very well. But it's a ULVZ with a diameter of 900 kilometers, a height of about 20 kilometers, and a velocity reduction of 20%, which cannot be explained by a thermal effect alone. You have to invoke either a solid kind of heterogeneity increase in iron content, most likely, or partial melt. And this is the data. I will skip it, but this is what the tomographic model would predict. This is the data, and you have to introduce this kind of feature which acts as a lens to explain it. More recently, we were able to do the same under the Iceland hotspot, or under the Iceland plume, with much better azimuthal coverage, much better coverage from every side. And this was a really interesting result because and I'll go quickly. Again, this is the observations, and you see some features here as a function of, as you sweep across in azimuth, you see decrease of amplitudes and you see some ripples. Nothing in the tomographic prediction, but if you introduce a ultra-low velocity zone as this, very broad again, 800 kilometers wide, you can explain both these features in the data. What is amazing about this is that we have observations from many sides, and the same model fits all sides, which means that this structure must be quite axisymmetric, at least to first order, which has led us to propose that the likely explanation for it is, in this root of the Iceland plume, is that it is due to partial melting rather than a solid inclusion. Which I'm ready to discuss further with anyone that wants to do that. And my kind of sort of prediction is that we probably will find such large ultra-low velocities beneath many, or if not all, of these very large plumes. To finish, I would like to still show that there are this one kind of columns of upwellings representing the upwelling flow from the base of the mantle. There may be others which we can't yet resolve, and in fact recently there is a work by Nelson and Grant that this is our model under Yellowstone. If you kind of squint, you might see something, but if you're not a believer, you wouldn't believe it. And now they are showing with a higher resolution work afforded by the presence of the dense US array network that you can actually see this kind of column coming up the lower mantle and also deflected around 1,000 kilometers. This is narrower and probably a different kind of upwelling than the ones that are based on the large low shear velocity provinces. So in conclusion, but I think we are now beyond the mantle plume kind of controversy. Maybe we should not call them mantle plumes, however, if mantle plume is a word that is really restricted to this concept in a purely thermal mantle. But the features that we see should inform, and I will not read it because I've said it all, should inform future geodynamic modeling and might help kind of discriminate between the so many models that can be produced with so many variables. And one last word is, just as this model of a plume that goes straight up to the top of the mantle is wrong, my current working hypothesis is that you have a very sluggish lower mantle where the upwelling flow is really limited to these discrete kind of columns, and the action is really in the top 1,000 kilometers of the mantle, with also recent evidence for the presence of secondary scale convection in that part of the mantle that I don't have time to discuss. And finally, the large low shear velocity provinces may not be piles of compact material, as some are modeling them right now, extending from the core mantle boundary to mid-lower mantle depths, but they're rather bundles of fat plumes in a halo of hotter than average background. Thank you.